In this lesson, we're going to explore the electrophilic addition reactions to conjugated and isolated dienes. Dienes are just molecules that have two alkenes, and because they're alkenes, they undergo the same electrophilic addition reactions. In a conjugated diene, the two alkenes are separated by one single bond. This creates a contiguous chain of four sp2 hybridized carbon atoms. Because dienes have two alkenes, each diene molecule could potentially react with two molecules of an electrophile. We describe that as reacting the diene with two equivalents of an electrophile. An equivalent is just an equimolar amount relative to the reactant. In the reactions of conjugated dienes, we're going to restrict the reactions to using one equivalent of the electrophile. When a conjugated diene is treated with one equivalent of an electrophile, like HBr, it can form two possible products. The first is the expected Markovnikov regioselective addition of the HBr molecule to either of the two alkenes. This is called the 1,2 addition product, because the H and the Br were added to adjacent carbons, or 1 and 2 relative to one another. The second product is likely a bit of a surprise. If you look closely, you can see that the hydrogen and the bromine were added to the opposite ends of the conjugated pi system, placing a double bond in between the double bonds of the reactant. This product is called the 1,4 addition product. If we arbitrarily assign the carbon that bonded to the hydrogen as carbon number 1, we can see that the bromine attached to carbon number 4, and that's why it's called a 1,4 addition product. The mechanism for the reaction is exactly the same as the reaction for an alkene with HBr. The first step is to protonate the alkene with the strong acid to form the most stable possible carbocation. Protonation of a conjugated diene can result in the formation of a resonance-stabilized allylic carbocation. In the allylic carbocation, the electron deficiency is shared over two carbons, and that means that this single carbocation actually has two carbons that are electrophilic. In the second step, the bromide acts as a nucleophile and can attack either the secondary carbon following the red curved arrow, which makes the expected 1,2 addition product. The bromide could also attack the primary electrophilic carbon following the green curved arrow, leading to the unexpected 1,4 addition product. It's important to recognize that in this reaction, only one carbocation is formed. The bromide isn't choosing to attack one carbocation over another. Rather, it is choosing to attack one carbon over another in that resonance-stabilized allylic carbocation. So which product is the major product? Well, it turns out that both products are actually favored, which admittedly is kind of like having a brother or sister and your parents saying, "Oh, you're both our favorite." So to see why both products are actually favored, we need to do an analysis of the energy changes that occur during the reaction, and that means a thermodynamic analysis and a kinetic analysis. So here is a free energy diagram of the reaction. A thermodynamic analysis of the reaction shows that the 1,4 addition product, here shown in green, is actually more stable than the 1,2 addition product, shown in red. If we look closely at the two products, we can see that the 1,4 addition product is a di-substituted alkene, and the 1,2 addition product is a mono-substituted alkene. And it turns out that alkenes are more stable when they're more highly substituted. And so the more highly substituted 1,4 addition product is the more stable product. And that means that at equilibrium, the 1,4 addition product in this case is going to be the major product. When we do a kinetic analysis of this reaction, we get a completely different result. You can see that the first step in this reaction is the slowest step, and so it's the rate-limiting step. But the rate of that step doesn't actually affect which product is favored. And that's because both products come from the exact same allylic carbocation formed in that first step. Which product is ultimately formed in the reaction is actually determined in the second step, and that's why it's referred to as the product determining step. If we look at the free energy diagram, we can see that the red pathway, which leads to the 1,2 addition product, is actually faster than the green pathway, which leads to the 1,4 addition product. As the bromide approaches the allylic carbocation, it will be attracted to either of the two electron-deficient carbons. If the bromide approaches the secondary carbon, then the transition state that forms will closely resemble a secondary carbocation. If the bromide approaches the primary carbon, then the transition state that forms will closely resemble a primary carbocation. And we know that secondary carbocations are more stable than primary carbocations. And by Hammond's postulate, that means that a transition state that looks a lot like a secondary carbocation will be more stable than a transition state that looks an awful lot like a primary carbocation. And that makes the red pathway, leading to the 1,2 addition product, the faster reaction. And that means that the 1,2 addition product is favored kinetically. And that's why both products of this reaction are favored. In this case, the 1,4 addition product is more stable and therefore favored thermodynamically, and the 1,2 addition product is formed more quickly and thus favored kinetically. Well, that doesn't actually answer the question of which product is the major product. And that is going to depend on whether the reaction is run under thermodynamic control or kinetic control. The thermodynamic product is the more stable product, and it's going to be favored by anything that promotes equilibration. And one thing that can promote equilibration is to have a high reaction temperature. The overall reaction here is exergonic, and that means that the products are more stable than the reactants. In order for the reaction to go backwards, more energy is required than in the forward reaction. So a higher temperature will provide that extra energy and allow the reaction to go backwards and forwards, favoring the thermodynamic product. In this specific reaction, the 1,4 addition product happened to be the thermodynamically favored product. But that's not always going to be the case. The thermodynamic product is simply the more stable product, and it can actually be the 1,2 or the 1,4 addition product. We just have to look at the two products and decide which one is more stable. And in these addition reactions to conjugated dienes, the more stable product will be the one that has the more highly substituted alkene. The kinetic product is the one that forms more quickly, and to induce kinetic control, we keep the temperatures low. That helps to prevent equilibration and allows the faster reaction to dominate. The kinetically favored product in an addition reaction to a conjugated diene is almost always the 1,2 addition product, and that's due to a phenomenon called the proximity effect. We tend to draw our mechanisms for reactions out kind of linearly, with lots of space around each molecule. But you have to remember that in reality, when molecules react, they are literally touching one another. As the pi bond of the diene approaches a molecule of HBr, it starts to break the pi bond and form a CH bond. And at the same time, the HBr bond starts to break. Once the bromide forms, it is very close to the other carbon of the alkene that was protonated. Attacking that carbon will lead to the 1,2 addition product, and it's very fast because the bromide has a very short distance to travel to attack that carbon. In order for the 1,4 addition to occur, the bromide has to travel down the length of the molecule and attack that other electrophilic carbon. And that travel takes time, and it makes the 1,4 addition reaction slower than the 1,2 addition. So the 1,2 addition is faster because of the proximity of the bromide to the 2 carbon relative to the 4 carbon once the bromide is formed. So in our first example, the butadiene molecule was symmetric. Both alkenes were identical, and so it didn't matter which alkene was protonated in the first step of the mechanism. The reaction gets a bit more complicated when the two alkenes of the diene are not exactly the same, and that's because different products will actually be formed based on which of the two alkenes is protonated in that first step of the reaction. Let's take a look at an example. You can see that this diene has two unique alkenes. You can definitely tell one from the other. And that means that the products that will form from an electrophilic addition reaction will depend on which alkene is protonated in the first step. In this case, the reaction is going through an acid-catalyzed hydration, but the process would be exactly the same for a hydrohalogenation. In order to figure out which alkene is more likely to protonate, we compare the stabilities of the allylic carbocations that would form from protonating each alkene. Protonation of the alkene on the left would lead to the formation of the allylic carbocation shown here. And if you look at those two resonance structures, you can see that one represents a secondary carbocation and the other a tertiary carbocation. Protonation of the alkene on the right would lead to the allylic carbocation shown here. And if you look at the two resonance structures, one represents a secondary carbocation and the other a primary carbocation. Because the allylic carbocation that forms from protonation of the left alkene is partially tertiary and partially secondary, it makes it more stable than the allylic carbocation that forms from protonation of the right alkene, which is part secondary and part primary. Because the carbocation that forms from protonation of the left alkene is more stable than the carbocation that forms from protonation of the right alkene, Hammond's postulate allows us to assert that protonating the left alkene will be faster than protonating the right alkene. Once we know which alkene is more likely to be protonated, we finish the reaction as we did before, having the nucleophile, in this case water, attack either of the two electrophilic carbons in that allylic carbocation. If we look at the products of the reaction, we can see that the left product is the 1,2 addition product because the H and the OH added to adjacent carbons, and the product on the right is the 1,4 addition product. Here, the hydrogen added to the leftmost carbon of the pi system and the OH to the rightmost carbon of the pi system. We know that the 1,2 addition product is typically the kinetically favored product because of the proximity effect. The thermodynamically favored product is simply the more stable product. And in this case, the more stable product also happens to be the 1,2 addition product. And that's because the 1,2 addition product is a tri-substituted alkene, and the 1,4 addition product is a di-substituted alkene, making it less stable. So in this case, whether the reaction was run under higher temperatures or lower temperatures wouldn't really affect the outcome. The 1,2 addition product would be favored in either case. Compared to conjugated dienes, the reactions of isolated dienes are fairly straightforward. Because the electrophilic addition reactions of isolated dienes cannot directly form allylic carbocations, they're not affected by resonance. The main concern with isolated dienes is determining which alkene will react, at least in cases where the two alkenes are distinct from one another. Which alkene of an isolated diene prefers to react actually depends on the mechanism of the reaction being performed. Reactions that go through a positively charged intermediate, like a carbocation or a polonium ion, will prefer to react the alkene with the most highly substituted carbon. And be very careful with that phrase. The alkene with the most highly substituted carbon is not always the most substituted alkene. The reason for this selectivity is simply that the most highly substituted carbon will better stabilize the positive charge that develops during the reaction. So in this example, we can see that we have an isolated diene with two unique alkenes, and the alkene on the right has the most highly substituted carbon of either of the alkenes. The right carbon of that alkene is more highly substituted than any of the other alkene carbons. The reaction being performed here is a hydrohalogenation, which goes through a carbocation intermediate, and so the reaction will occur preferentially on the rightmost alkene, the alkene with the most highly substituted carbon. From there, we simply perform the reaction as we would for any other alkene. Hydrohalogenation is Markovnikov regioselective, and so the bromine is placed on the more substituted carbon of the alkene and the hydrogen on the less substituted carbon. And of course, if an excess of HBr were used, both alkenes would simply do a Markovnikov regioselective addition to give a dihalide. If the reaction being performed on an isolated diene does not go through a positively charged intermediate, like a carbocation or a polonium ion, then the reaction will prefer to react the less substituted alkene. Because there's no need to stabilize a positive charge developing during the reaction, the selectivity is controlled by a combination of alkene stability and sterics. Less substituted alkenes are less stable than more highly substituted alkenes, and that makes them generally more reactive. Less substituted alkenes are also sterically less hindered, allowing electrophiles to approach them more easily, again leading to a faster reaction. So if we look at this example, we have the same isolated diene that we had up above. The alkene on the left is monosubstituted, and the alkene on the right is tri-substituted. The reaction being performed is a hydroboration oxidation, a reaction that does not involve the formation of any positively charged intermediates. And that means that the reaction will preferentially occur on the less substituted alkene on the left. From there, we again perform the reaction as we would for any other alkene. Hydroboration oxidation is an anti-Markovnikov regioselective addition of water. So we place the hydroxy group on the less substituted carbon of the alkene and the hydrogen on the more substituted carbon.